Hello, everyone. Welcome to today's webinar. Thank you for joining us to talk about our topic, reducing water temperature in legacy hydronic systems. My name is Kevin, and I'll be getting us started today. As usual, a recorded version of this webinar is going to be available on our website, our YouTube page, and it's going to be linked in our post-webinar email. Before we get to today's topic, I want to go over a couple housekeeping items. In the top right, there is a questions tab. If you're experiencing any issues, please utilize this function to reach out to our team. If you have any questions throughout this process, that's where you're going to go to get those answered as well. Do not hesitate to ask away. In that same menu, you'll find settings tab for any audio or session changes that may need to be made. Lastly, we're doing something a little different this time. At the conclusion of this webinar, there's going to be a survey prompt with 8 quick questions. If your input's super important to us, if you have a couple minutes and don't mind answering those, we would greatly appreciate it afterwards. Again, my name is Kevin. I'm our events and marketing strategist here at Intertech. We also have our director of product management, Jeremy Vonderhaar, with us, our quality assurance manager, Justin Job, and last but not least, John Sigenthaler, principal engineer at Appropriate Designs. We all just got back from AHR in Orlando. If you were there and stopped by to see us, I just want to say thank you. We had a great time talking to everyone and showing off new revisions of both our Advantage air-to-water unit and our variable speed water-to-water unit, which Justin will be talking about a little bit more next month. For those of you just joining us, welcome and thank you for being here. I'm going to hand things off to John to dive into today's topic. John, the floor is yours.
Thanks, Kevin. Glad to be with you folks, coming to you from a very snow-covered upstate New York today. Good day to talk about water temperatures and hydronic heating systems, and specifically, what can be done when we have an existing or what we refer to as a legacy hydronic system. What can be done to bring the water temperature down? And that's certainly relevant to either water-to-water heat pumps, air-to-water heat pumps. It's also relevant to modulating condensing boilers. And you can see in this slide here, I've just picked several contemporary heat sources for hydronics. And in the upper left there, it's just a ModCon boiler. And ModCon boilers count on the condensation of the water vapor that's formed during combustion. In a standard boiler, what I refer to as a conventional boiler, that water vapor that's produced just goes up the vent, out the chimney. And you're actually losing roughly about 10% of the thermal energy that's created in the combustion process as that goes out. And what this graph is showing you here in this upper left corner, if we start over on the far right at 200 degrees, you can see as we bring the temperature of the water coming into the boiler down, the efficiency is slowly increasing, and it gets up to just about 87%. And that's where the flue gases, the water vapor specifically in the flue gas, starts to condense. And for every pound of water vapor that condenses back into a liquid, you liberate about 970 BTUs. So there's a tremendous amount of heat available. And you can see that the efficiency climbs pretty fast as you continue to lower the water temperature in the boiler. And this is why, for example, radiant floor systems, low temperature radiant floor systems are well matched to these types of boilers. Now, down below it is a solar thermal collector. This market is pretty small right now. It had a couple strong periods of time, but with solar thermal collectors, whether they're doing domestic water heating or even space heating, you can see on the graph here, as that inlet temperature going into the collector goes down, the thermal efficiency goes up. So again, low water temperatures are going to benefit the efficiency or the performance of those collectors. Now, up in the right here, this is a water-to-water heat pump. And over there, I've plotted out just a representative graph where you can see entering load water temperature. This would be the temperature of the water coming back from your hydronic distribution system, coming into the heat pump. And as that temperature goes down, you can see the COP numbers on the vertical scale definitely go up. And then finally, lower right corner, we've got the Advantage air-to-water heat pump from Intertech. And there's a graph there. There's 3 curves. The blue curve is for a leaving load temperature, LLT, leaving load temperature of 95 degrees. And then the bottom graph right there, that would be the outdoor air temperature. So as it gets warmer outside, obviously the COPs are going up. But if you compare the blue curve, the red curve, and the black curve is when we're asking the heat pump for 131 degree temperature. So you can see the COPs go down as the leaving temperature goes up. So the common message with all these heat sources today is that lower water temperatures benefit the efficiency of the heat source. Now, again, the heat emitters in the system will have tremendous influence over the water temperature the system operates at. So with any heat emitter, the output always goes down as the water temperature inside the heat emitter goes down. I'm sure just about everybody knows that, but it's worth stating. One thing that I found over the years that not everybody understands is that there is always some output, provided the supply water temperature is above the room air temperature. I've had people say that, for example, fin tube baseboard doesn't work below 140 degrees. Well, the rating tables don't go below 140 degrees, but as long as there's a temperature difference between the water in a heat emitter and the room air temperature, there's going to be some output. And we'll get into the graph that shows what that output is for fin tube at low water temperatures. And then finally, one of the very fundamental things about hydronic design, there's always a trade-off between the total surface area of the heat emitters. If you imagine your system, whether it's floor heating, panel radiators, baseboard, fan coils, or some mix, the more surface area you have, the lower the supply water temperature can be for a given rate of heat output. Okay? So more heat emitter area always brings the water temperature down. And this is a chart that I've shown in some of the past webinars. Basically, across the bottom are water temperatures, supply water temperatures. And then these yellow bars just represent a typical range of water temperature for a certain type of heat emitter. And again, over the last several decades, the North American market, if you roll back into the 1950s, 1960s, it was largely about high temperatures, 180, even over 200 degrees Fahrenheit. Fuel was inexpensive. It was less expensive to build smaller heat emitters and go to higher water temperatures. And that trend has certainly shifted as we looked at modern heat sources like heat pumps. And then over on the left side, you can see there's several types of radiant panels that are well within the operating range. And I've just kind of drawn a line there and boxed this area in. I would suggest to you any hydronic system that you're designing today for space heating, you design it in such a way that at design load, you don't need a water temperature above 120 degrees Fahrenheit. Again, that is not an ASHRAE standard. To my knowledge, it's not in a code, but it's a good target. It certainly brings your distribution system within the range of not only heat pumps, but good performance on modulated condensing boilers, good performance from thermal storage systems as the water temperature in the storage system goes down. And I like to use the term, it future-proofs your system. So yes, today we could design a hydronic system legally around 200 degree water, but 5 years from now, you may not have the ability to have a heat source that can provide that for you. I don't know that to be assured, but looking down the road, if you design around a reasonably low water temperature today, you're pretty much assured that these future heat sources, be they some type of boiler, some type of heat pump, some type of combination of thermal storage, heat pumps, whatever it is, you have compatibility. So you don't have to go back and start modifying the system. Okay. Now, as far as bringing that water temperature down in an existing system, there's really two fundamental approaches to it. One is to reduce the design load of the building. And I'll show you a pretty simple formula that will let you evaluate if I reduce the building load by, let's say, 30%, how much of a change in the supply water temperature will I get? So anytime you build a tighter or better insulated thermal envelope, you're able to bring the water temperature down. The other is to add heat emitters. And this goes right back to the idea, the more surface area we have, the lower the water temperature can be for a given output. And it doesn't have to be one or the other. It can be a combination of both. And every situation is a little different. You have to basically do a site visit, look at the probabilities or possibilities of reducing load. And again, reducing load can be done air sealing, more insulation, improved windows, anything that affects that thermal envelope that'll bring that load down is plausible. Adding heat emitters in some cases is relatively straightforward. We're going to talk about some pipe configurations for that. In other cases, it's very difficult, especially with fin tube, just due to the amount of wall area that you need. So that's a little path out here. This is a pretty simple formula. This allows you to calculate a new supply water temperature based on an existing load and an existing supply water temperature. It allows you to find out how much lower can I bring that water temperature. So let's just do an example. We're going to assume we have a building. It has a design load of 100,000 BTUs per hour based on maintaining an indoor temperature of 70 degrees. The existing hydronic system uses standard fin tube baseboard. And let's just say that the baseboard was sized around 180 degree water temperature to provide that 100,000 BTUs at design load. Now, let's say we've done improvements to the thermal envelope of the building. We've reduced the load from 100,000 BTUs per hour to 70,000. So we've got a 30% reduction in load. Again, it doesn't specify how that's done. It could be anything that we've talked about: insulation, air sealing, windows, so forth. So let's calculate that new supply temperature just based on these assumptions. You could see this is down at the bottom there. We're trying to maintain 70 degrees inside. Our new load is 70,000. Our existing load prior to those envelope improvements was 100,000. And then in parentheses there, we've got 180 minus 70. The 180 was the original supply water temperature. And again, 70 would be the air temperature we're trying to maintain. You run that through the calculator, we get 147 degrees is our new temperature. So over on the right, I just made a plot. And this is an outdoor reset schedule. So the red line up, the upper line there, shows that when it was 0 degrees outside, let's assume that was our outdoor design temperature, we needed 180 degree water. Okay, so that was our design point. Based on a 30% load reduction, we've now reduced that down to 147 at design. And the reason I wanted to show the reset line is that, remember, if you're only at design load conditions, roughly 2, maybe 2.5% of a typical winter. There are many more hours where you're at a partial load condition. For example, maybe it's between 20 and 30 degrees outside. If it was 30 degrees outside and we reduced that load by 30%, we needed 147 at design. Well, we only need maybe about 115, something like that at 30 degrees. So you can see under partial load conditions, we have water temperatures, even with an existing baseboard system, that are well within the range of what modern heat pumps can provide, both water-to-water geothermal and air-to-water heat pumps. Now,
real quick, John.
Yes.
Since you're talking about baseboards here, we did have a question in the chat here, and the question was, if the water temp is lower than the air temp, will the fin tube baseboard cool the room? Could an air to water heat pump be used with existing baseboard systems to provide any amount of cooling without adding ductwork? You got any?
It's a great question. It's one I'm assuming a lot of people think about, but you're going into kind of dangerous territory there, as I'm sure you should appreciate. The problem you get into with chilled water and fin tube is, if as soon as that water temperature gets below the dew point of the room air, you're going to form condensation on the tube and on the fins. And a fin tube baseboard it has no way to capture that condensate. So I can answer the question this way. Yes, you might get some sensible cooling, But the only way that you could potentially do that, and I don't recommend this by any measure, but the only way you could potentially do that with any success would be to know and monitor and control based on room dew point temperature and make sure that that chill water temperature never goes below the dew point. Now, the geometry of the fin tube at the floor really is not well suited for that as well. There have been some fin tube elements that have been used in what's called valence cooling. You could check it out with, there was a company, Edwards Engineering in New Jersey, that has had this system out for years. It's basically a fin tube that goes up near the ceiling on the wall, and it actually has a valence that goes around it that captures the condensate. So there's no fans involved. Again, the potential long-term problem or challenge, I should say, is whenever you have condensate, you're going to have the potential for mildew growth. So the hygiene of that system is critical. So to go back to your question on it, or the viewer's question, I would say don't do it. What do you think?
Yeah, and that was kind of with water temps that warm, the capacity of cooling you're going to get out of that is, and on the floor, there's just a lot of reasons I don't really think that it would be beneficial to risk it.
Absolutely.
We do have one other question here real quick. Your thoughts on adding small fans to existing large cast iron radiators to increase heat output at lower water temps?
Yeah, I mean, it would. The limiting factor on a radiator is basically convection. And anytime you improve the airflow rate over a surface, you're going to improve the convective heat transfer. So yes, in theory, you would get more output. I don't know how you would evaluate something like that. There are some panel radiators. We don't see much in North America, but in Europe, one of the trends, there are several panel radiators that actually do have what I'll call micro fans built into them, specifically for that purpose. As the water temperatures go down, the natural convective heat output also goes down. So what they're doing with these small little fans, and when I say small, these little fans run on about 1.5 watts each. They're like the fan in your desktop computer. They're enhancing convection at low water temperature. So yeah, you could run a fan and potentially squeeze a little more heat out of that radiator. How you would make that work aesthetically from a sound standpoint and so forth, I'll leave that up to somebody else. Any other questions?
No, that's it right at the moment.
It's good. Okay. Those were good questions, by the way. And, people are definitely thinking about these things. So we talked about reducing water temperature. Now, one of the things that you want to appreciate about the heating load over a season is that it's split up over a wide range of outdoor temperatures. And this is a graph that is called bin temperature data. And it's for Syracuse, New York, upstate New York. It's a relatively cold climate. It's around 6,600 degree days a year. And all those blue bars are, if you look at the outdoor temperatures, and across the bottom, you'll see they're broken up into 5-degree Fahrenheit increments. So it is possible to look up for hundreds of locations in North America, actually all over the globe, bin temperature data. There's a database that's free to access. It's called the National Solar Radiation Database. It's maintained by National Renewable Energy Labs. So if you Google that, again, National Solar Radiation Database, they have just huge amounts of data on not only air temperatures, but all types of atmospheric conditions. But anyway, what we're looking at here is this spread of outdoor air temperatures for an average winter in Syracuse. Now, there's another way you can plot that data. This is called a heating duration curve. And what it is on the vertical axis is just percent of design load. So we go from 0 up to that red line there is 100% of design load. You could also put numbers on the vertical axis that would be in actual BTUs per hour. So for example, 100% on a house might be, I'm picking a number here, maybe 40,000 BTUs per hour. And then on the horizontal axis, this is the number of hours in a year when the design load is greater than or equal to some percentage of the load on the vertical axis. So, for example, if I ask the question, how many hours per year are we at or above 40% of design load? Over on the left, you can find 40, follow the green line over to the curve and then down. Looks like roughly 3,600 hours a year we're at or above 40% of design load. Now, you might say, why plot the data like this? Well, that yellow area that you see under the curve, that area is proportional to the total seasonal space heating energy requirement. So mathematically, that yellow area represents the total complete heating season energy usage. And one of the ways you can put that together with performance data on your heat emitters, for example, how much of the seasonal heating energy is required above 120 degrees Fahrenheit? Now, this is in the context of that example we just did, where we had a 30% reduction in load, and we know that at design load, we need 147 degrees. So all I'm doing here is I'm taking the graph with the yellow area, and I'm moving it over to the right there, and I'm scaling it so that 100% design load lines up with 147 degree water temperature on the graph that's in the middle there. And then if you, again, go to the middle graph, go over to the vertical axis, and you'll see where that green dashed line intersects that vertical axis at 120 degrees. Now, remember, I'm asking how much of the seasonal energy is required above 120 degrees. So if we follow that line across, and it goes across the heating duration curve, it's dividing the heating duration curve into the blue area up at the top and the green area down below. And the green area represents about 93.5% of the total seasonal energy that we can supply at or below 120 degrees. The blue area is only the remaining 6.5% of that seasonal energy. And that's where we have to be above 120 degrees Fahrenheit. Okay. And the takeaway from this is that even though we need 147 degree Fahrenheit at design load, at 120 degrees or less, we can still supply about 93% of our energy. So think about that in the context of a heat pump. That 120 degrees is well within current generation heat pump technology, be it R410A or R32 or R454B, can easily operate at those temperatures. So we're still getting the vast majority of our seasonal energy supplied by the heat pump. And if it was a dual fuel application where we had a boiler as either an existing heat source or backup, it would only be supplying roughly about 6.5% of our energy, which builds a good case for, leaving that boiler in the system if it's there. If it was a system that had an electric resistance heating element in it, that element is only going to supply about 6.5% of that seasonal energy. So I think that's a very good proposition today, especially when we have an existing boiler in the system, and we've done a past webinar on that subject. Okay. Now, again, people oftentimes they may assume that, gee, I have fin tube. Somebody has told me I need at least 180 degree water, so heat pump can't work. And that's not the case. Okay. You have to put fin tube in a context. Fin tube was designed back in the 1930s. It was designed to be the modern contemporary answer to cast iron radiators. Okay. So obviously a lot lighter, easier to move around and so forth compared to cast iron. But again, think of the energy prices at that time. Mid 20th century energy prices were pretty low, and most heating systems, hydronic systems, were designed around high water temperatures, and 160 to 200 degrees was a typical range. Okay. Now, on the right side there, you can see there's a graph. And that's for standard residential fin tube, like you see in the photograph there. And it shows you water temperature on the bottom versus heat output in BTUs per hour per foot of fin tube. Remember, some enclosures like this, you want to take a close look if you're evaluating it. Sometimes the enclosures just run along the wall like that just for aesthetics. There might only be a copper tube in there with no fins on it. And that's going to put out a little bit of heat, maybe 5 to 10% of what a fin tube will put out. So this would be BTUs per hour per foot of fin tube. And it's an easy graph to work with. Just it's based on a entering air temperature at the floor level of 65 degrees Fahrenheit. So for example, at 145 degree water temperature, and by the way, this would be the average water temperature. We go up to the curve and then we read over a little under 300 BTUs per hour per foot. Again, standard residential fin tube, 2 1/4 inch square fins, usually 3/4 inch tubing. Okay. And down here, just this note, fin tube output at 120 degrees is only about 30% of its output at 200. Okay. Now, the procedure I'm going to show you is a calculation of how much fin tube, standard fin tube, residential grade fin tube I would have to add to a system to bring the water temperature down to some predetermined level, be it 120 or 110, so forth. Again, it's based on standard residential fin tube, 2 1/4 inch square. If you look up some specs on the baseboard, you'll find what are called IBR ratings. And typically, you're going to get about 600 BTUs per hour per foot at 200 degree water. So here's the steps really quick. You're going to do a heat load calculation to get the building's design heat load. And then you're going to take an inventory. How much existing fin tube is in the system? We're going to call that LE, length existing. Okay. Decide how much lower you want the water temperature to be. And it says here, estimate lower average circuit water temperature by subtracting 5 to 10 degrees from supply temperature. And just as a couple guidelines here, if your circuit is operating at more than 2 gallons per minute, I'm suggesting you subtract 5 degrees from the supply temperature to get an estimate for the average water temperature. Remember that graph I showed you was based on average water temperature, not supply. If your circuit's operating at a relatively low flow rate, you're going to have a larger delta T. I suggest you subtract 10 degrees. Again, what we're trying to do is get to an estimate of average water temperature. Then you're going to go to the graph, okay? So as an example, let's say that we determine our average water temperature was 115 degrees Fahrenheit, and we just go up to the red curve and then we read over to the left. Looks like we're a little under 150 BTUs per hour per foot of fin tube, okay? And then finally, now that we know what our fin tube is capable of at that low water temperature, we can use this formula down at the bottom where we take our design load, we divide it by the output of the baseboard at the lower water temperature. In this case, I believe it was 147 BTUs per hour per foot, something like that. And then we subtract the length of the existing baseboard, and this will give you how much baseboard you have to add. So let's run through a quick example on it again. Let's say we had a design load of 40,000 BTUs per hour. We've totaled up the fin length of the baseboard. We've got 120 feet of standard residential fin tube. The goal is to get the supply water temperature to 120 degrees at design load using the same type of baseboard. And assuming the temperature drop of the distribution system is 10 degrees, figure out how much baseboard we have to add. So again, quickly, design load was 40,000. We've inventoried how much existing baseboard we have, 120 feet. We want to get it down to a design supply temperature of 120. And we're going to subtract, if we have a 10-degree drop in the circuit as it's operating, we're going to subtract half of that. Because, again, we're looking for the average water temperature. So it's going to be 115. We use our graph. We already looked at this line here at 115. We're getting 146 BTUs per hour per foot of baseboard. We plug that into our formula and look at what we get. We need 154 additional feet of baseboard. Now, you're probably thinking, are you kidding me? Where am I going to put 154 additional feet? This is not total feet. This is how much you have to add to what you already have. And bottom line is, it's possible but very improbable that you're going to have wall space to do this. I have had people ask me, can I double stack the fin tube? I tell them don't do that. Not only quickly, but the output from the lower baseboard is going to be warmer air going into the upper baseboard, and that's going to reduce its output. So it becomes very impractical to do that with standard baseboard. Now, another option that you do have would be to go to high output baseboard. And one of the products that's out there, here's a photo down at the bottom here, where you see the 2 copper tubes. That's called heating edge baseboard. And, it's to use an overused phrase, it's not rocket science. That's 3 times the fin area and 2 times the tube. They're simply putting a much more effective heat exchanger inside a nominal enclosure that's about the same size as standard baseboard. The graph up at the top shows you it's quite a difference in output, roughly twice the output, because of the greater area of the fins and the tubing as well. So for that, the steps are very, very similar. It's a slightly different formula that you're going to use. And there's the formula. If we take the design load, we're going to subtract the multiplication of the output of the baseboard, existing baseboard, that would be the standard fin tube, at the low water temperature. We looked that up on the graph over here at the lower curve. And then we're going to design by the output of the high output baseboard at that low temperature. So we just did the algebra on that formula. And again, I'll run you through an example. We'll take the same house. It's got a 40,000 BTU per hour design load. It's got 120 feet of standard baseboard. We want to bring the water temperature at design load down to 120 degrees. We're going to assume that the circuit has a 10-degree drop from supply to return. And we've already looked up the output of the existing baseboard at 115-degree average water temperature. It's 146 BTUs per hour per foot. So we just plug the numbers into the formula, and as we would expect, it's a shorter length. Instead of 154 feet of baseboard, we're down to 67 feet of baseboard. But I would still tell you, where are you going to put it? So, it's not that these exercises are without some merit, because there may be situations where you can accommodate this. But the key thing with fin tube is wall length. Where am I going to put this? Especially in kitchens, bathrooms, where you often have cabinets that take up a good portion of that wall space. So anyway, those are tools that you can use if you're considering, how do I add fin tube, be it standard or the high output, to bring that water temperature down. But there's other options. And one of the options...
You've got a question here, John?
Yep.
So when measuring fin tube, how's sequence considered?
You really don't have to for those calculations. You're looking at the house basically as a block, as a single entity. You're just looking at the total. The sequence, in a sense, would be taken into account by the temperature drop that you're getting. Now, to the point of the question, there was nothing in there that guaranteed that if you have, for example, a series string of baseboards, you have different loads in each room. There are different ways that baseboard can be sized. Oftentimes, baseboard was sized by simply saying, I take an average water temperature, I go to the baseboard rating table, I look up an output, and then I just divide that output into the load of each room to get how much I need. So they've actually sized the baseboard, assuming every baseboard operates at the average water temperature. That's really not the case. In a series string like that, every downstream baseboard is getting water temperature that's a little bit cooler than the upstream baseboard. There's more accurate ways to do that. But those calculations we just went through are kind of I don't want to say this, kind of a macro picture of, is it even feasible to consider adding more fin tube or are the lengths simply not something I can accommodate in the project?
In most projects that I see, when people are wanting to convert a home to a heat pump technology, one of the goals of that is to add cooling capability. And most baseboard homes, or the vast majority of them anyway, generally were not set up with cooling originally.
Right.
And so having, whether it's putting ductwork in or putting fan coils in, you can certainly increase your heat output capability. Those devices are just a lot more efficient at moving BTUs on the heating side as well. So you can decrease your overall water temp if you add some sort of fan coil device, and you're going to pretty much across the board going to have to do something like that to add cooling anyway.
Correct. Good point. So if you're adding cooling, you don't really want to look at fin tube. You don't actually want to look at panel radiators. Now, you could look at console fan coil units, so kind of on a room by room basis, or you could look at a central air handler and ducting. You might look at a high static pressure air handler and use the 2-inch flex ducting. That is easier to accommodate around existing structures. But absolutely, if you're going to bring cooling into the picture, you need to have a device that can not only operate in heating, but can also operate with chilled water. And to do that, it has to have a way to collect the condensate, whether it's a drip pan in a console fan coil, or whether it's a drip pan in a central air handler. So that's an excellent point. I'm focusing a little bit more on the heating side, but you're absolutely correct on you can add air handlers and build surface area of heat emitter that way.
Yeah, I just think in today's world, you would be better served, I feel like, instead of trying to add more baseboard emitters to a home. I think you could achieve the same goal by getting lower water temperatures, add more heating capability, and get cooling all in the same, with whatever device you're adding, whether that be central air handler or individual fan coils, high wall, low wall mounted. There's a whole ton of options out there. We did have one other question about outdoor reset controls. It's kind of a wide open question, and we could probably spend an hour just talking about outdoor reset controls.
Okay.
But real quick, you got any tips or considerations on outdoor reset?
Well, I definitely like outdoor reset because what it does is it doesn't force the heat pump to operate at conditions any higher, to operate at water temperatures any higher than necessary. So anytime we can bring that water temperature down and still adequately heat the building, and that's the whole basis of outdoor reset, we're going to improve the efficiency of the heat pump.
Yeah.
And your units have controls that can do that automatically. It's not that they need to have an external controller to do that.
Correct. Yeah.
The WV and the AV unit both have that as an option in a control.
Yeah, it's all built in. So you just select the high water temperature and the low point water temperature, and then we have 15 different curves in between there on how aggressively you want to achieve those temperatures. So, and then we also offer dual fuel options, so you could bring a backup boiler into this or electric heating elements. But definitely outdoor reset is a beneficial thing for sure.
Sure is, especially with heat pumps. So I encourage anybody designing around hydronic heat pumps to bring outdoor reset into the picture. Okay, Hal, I do want, I'm going to go on here with panel rads. Just again, panel radiators are designed for space heating, but the technique that I'm going to show you, the calculations are very simple. And to Justin's point, whether it's a panel radiator or a console fan coil unit, it's the same concept as far as how much do I need. So just from the heating standpoint, I wanted to give you a reason to consider panel radiators. A 2-foot by 4-foot panel radiator is equivalent to 23 feet of residential fin tube, and that's at an average water temperature of 110 degrees. So from a space standpoint, this is much more practical. Again, these are not designed for cooling, just for heating. But it shows you that, as I say, from a practical standpoint, it's more likely you could accommodate a panel radiator compared to trying to do it with fin tube. And just again, as you go down in water temperature, the size of the radiator goes up. It's that trade-off we talked about at the beginning. So you can get larger radiators, both height and length. You can also get different thicknesses. And I just want to show you an example. Here's a panel rad that is nominally about 2 feet by 4 feet. You see the two tubes coming up from the bottom. That's 1/2-inch PEX aluminum PEX tubing. Over in the upper right corner, that's a thermostatic valve that allows you to control the output of that radiator. But this is basically what they look like. And when you, or if you are evaluating these, you're going to see tables similar to the one in the left side there. And there are most manufacturers that offer these, and there are several that sell these products in North America. And they'll offer these in different thicknesses. It's common to see 3 different thicknesses where you go from 1 water plate to 2 to 3. You're basically just building a thicker sandwich of fins, which is going to give you more surface area. And then as you look at the numbers in the table, the blue numbers represent the height, and the red numbers across the top represent the length. And then the black numbers that are in the table, those are the BTUs per hour output. But it's important to understand that's at an average water temperature of 180 degrees Fahrenheit and a room temperature of 68. So manufacturers tend to rate these at these high temperatures simply because they have bigger numbers. And certainly if you're applying these with a boiler and operating at those temperatures, that's valid data. Now the question is, well, I don't want to run it at 180. I want to run it at maybe a supply temperature of 120. How do I know how many of these I need? Okay. Well, there's a correction factor. And the correction factor is based on the average water temperature that you want to operate these at, the room air temperature. You take the difference between those two. We subtract the room air from the average water temperature, and you raise that to a power. I'll just round it off to 1.3, okay? And then you multiply by that 0.00207. That gives you a correction factor. And you can also use the graph. The graph and the formula are the same in terms of the values they're going to give you. You take that correction factor and you multiply it by the values that are in the table, the black numbers in the table, and that'll give you the output at these lower temperatures. And just to kind of jump ahead, if we took this radiator and it produced a certain amount of output, that would be, this radiator would be 24 by 48, and it's got 2 water plates on it, so it's 9,500 BTUs per hour. If we were to run that with a supply temperature of 140, we're going to get a little under half of that output. If we bring it down to a supply temperature of 120, we're getting about a little more than a quarter of the output. So yeah, the output drops substantially at these temperatures. But that being said, keep in mind that a panel like this actual photograph was in a bedroom. And it's a fairly good sized bedroom, and that's the only heat emitter. And that's actually running no higher than about 110 degree water temperature. That is actually being supplied by a water to water heat pump. So these are applicable to low water temperature conditions. You simply are going to be using larger panels to accommodate that. So we're back to the trade-off between surface area and water temperature. Now, how many panels do I need? Well, there's a really simple formula, and this would be this exact same procedure you'd use for a fan coil. We're going to take the design load that we need to supply. We're going to subtract the output of the existing heat emitters. We're assuming we're going to leave those existing heat emitters in place. And that difference is what we have to provide through the new heat emitters, whether it's a panel rad or a fan coil, okay? So basically have to go to manufacturer's data at this point. When I say a fan coil, there's probably dozens, if not multiple dozens of fan coils that are available out there. And they have different size coils, they have different size blowers. And the only way to know what the output is going to be at a given temperature is to go to the manufacturer's data. And I just put a note, remember that the average water temperature is going to be about 5 to 10 degrees lower than supply temperature. Okay. So again, let's do it for panel radiators. Let's assume we had that same house, 40,000 BTUs per hour. Distribution system's got 120 feet of existing fin tube. We want the water temperature to be 120 degrees. And let's say that we've decided to go, and just for the sake of illustration, I took the 2-foot by 6-foot panel. That's a pretty big panel, but at that low water temperature, it puts out about 4,200 BTUs per hour. So how many panels do we need? Well, we just use the formula. We take the existing, we'll start with the load, 40,000. We subtract 120 feet of fin tube. At that low water temperature, it's putting out 146 BTUs per hour per foot. And it tells us we need to make up roughly 22,500 BTUs per hour. So we just divide that by the output of that particular panel that I've assumed, and we need 5.3 of those radiators. Now, that could be a fan coil. If that fan coil put out 4,233 BTUs per hour at that same temperature, the math would be identical. So it tells you basically, I need 5.3, and obviously you're not going to buy 6 and cut one off. You could either go to 6 of them and go to a slightly lower water temperature, or use 5 and go to a slightly higher water temperature. So you can see this is pretty simple from a mathematical standpoint. Again, it's based on leaving everything that's there in place. We're essentially just calculating how much additional surface area, be it a panel rad or be it a fan coil unit, or if you're going to use a central ducted air handler, again, you would look up what is the output of that air handler at that low water temperature, divide that into the deficit, I'll call it, the 22,480 BTUs per hour that we have to make up, and that would tell you how many of those you would need. Let's talk about the pipe geometry a little bit. These are two common legacy pipe arrangements. The top one is just a simple series loop where you come out of the boiler, typically a circulator, you go through all the fin tube in one long circuit, come back to the boiler. The lower one is sometimes seen, it's called a split series circuit. The idea is that one of these loops goes around one side of the house, the other one goes around the other side of the house, and then they come back together at the boiler. But all of these are, especially the upper one, the baseboards are arranged in series. And I'll be frank, series baseboard, it made sense probably in the 50s or 60s. You can still do it today, but honestly, you're giving up a lot when you go to series compared to going to some kind of a parallel distribution system. If the baseboard isn't sized properly, if the room loads weren't calculated properly, you may not necessarily proportion the right amount of fin tube to a particular room load, and you really can't do much about that once this is all put together. There are dampers that you can close that will reduce the output somewhat, but if it's undersized, there's really nothing you can do that would allow you to bring that one room output up without overheating the other rooms. So series piping loops are really, they're very much legacy in terms of modern hydronic design. So here's an approach that I think makes sense. It's essentially you are starting with that series baseboard, and we're going to modify it over into it's a combination of series and parallel. You can see if you just pick one of these circuits, say that top circuit, the black baseboard there, I've labeled it existing baseboard, and then the orange one with the bigger fins, I've labeled it added baseboard. So, but that's just one of 4 circuits now. And what we've done is we have cut the existing distribution system where we can access it. And we've added that extra baseboard. And then we're going to bring that circuit back to a manifold using 1/2-inch PEX or PEX aluminum PEX. And that's a much easier tube to install compared to trying to do everything with copper. I don't want to say you can't do it with copper, but it's going to be quite a bit more time consuming and definitely more expensive than doing it with PEX. And you might say, well, gee, it was a 3/4 inch pipe going through the baseboard. How come I could do it with 1/2 inch PEX? Well, it's because you're only doing a portion of the system. Everything isn't all in series at this point. And just for illustration, I've added a couple panel radiators at the end of the 2 lower circuits. And then again, I've transitioned back to 1/2 inch PEX, brought that back to a manifold. Excuse me. So parallel piping, one of the things it does for you is it reduces, or in some cases eliminates, that sequential temperature drop that one of the questions was referring to earlier on. Now, true, we do still have some heat emitters in series here, but compared to having all the heat emitters in series, we're getting closer to, we're not reducing the sequential temperature drop completely, but we're getting closer to having circuits that operate at similar average water temperatures. The other thing we can do that we cannot do well with the series loop is we get some balancing options. We can adjust the flow rates, either at the manifold or sometimes right at, for example, the valve that's in a panel radiator. And the transition fittings are readily available. And I put a couple in here. These are going from 3/4 inch copper over to 1/2 inch PEX aluminum PEX. There are similar adapters for PEX. So making the transition between that typical 3/4 inch copper tubing and 1/2 inch PEX or PEX aluminum PEX, the fittings are out there to do that. Here's one arrangement. This is assuming that we've got, let's say, assuming we've got a boiler in place, all right? So I am showing a hydraulic separator. Now, there is a direct-to-load approach on this, too, that would eliminate that hydraulic separator and actually eliminate both the circulators. If you're using, for example, the Enertech AV system, the circulator is already built in, and you could go direct-to-load from the indoor module of the AV system directly over to this manifold. I'm showing thermostatic radiator valves, and these are just some of the geometries that are available. You can get radiator valves in the upper left there where you can actually have a wall adjustment. That's a capillary tube that's coiled up there. Don't cut that and try to put it back together with a wire nut. I have an architect friend that tried that. Doesn't work. And the valve body itself, you want to put that valve body where you can access it. Don't bury it in a wall cavity where, you'll forget where it is. You can't access it. It's not that you have to access it commonly, but you should have it so that it could be accessed if necessary. In the upper right, that's a classic valve body with a thermostatic operator head added to it. That could go, for example, inside the enclosure of a fin tube. And if it's a panel radiator, you can order panel radiators where the valve body is built right in and the thermostatic operator is just added to it. Now, the thing you can't do with these thermostatic valves, these are non-electric. There's no switches to signal when the heat pump operates. It's counting on these thermostatic operators to be the temperature regulators for the individual spaces that the system serves. But if you want to use thermostats and you need end switches, for example, to tell the heat pump when to turn on, the piping geometry is exactly the same. The difference is now we're using manifold valve actuators. These are little 24-volt operated heat motors that screw onto the valves on the manifold, and they would just be wired back to a 24-volt thermostat. Typically today, you would bring all the thermostats into some kind of a multi-zone relay center, and then the output of that relay center would drive these valve actuators. And again, over on the left side, I'm showing a hydraulic separator. It's useful if you have a boiler in there. It acts on, it basically isolates the pressure dynamics that's going on in the boiler from the pressure dynamics that are going on out in the distribution system. If you were doing this with the AV system or the WV system, which are both designed for direct to load, the hydraulic separator would go away and those two circulators would also go away. You would just be using the indoor unit of the AV system or the WV unit, and it's going to have its own internal circulator. So again, they have put together, prepackaged, pre-engineered what could be built in the field. But again, in the case of the boiler, this would be a way to do it. Now, one of the things I do want to caution you about, if you're leaving a conventional boiler in the system and you're going to use this as backup, and by conventional, we mean a boiler that was not intended to operate with sustained flue gas condensation. And down below there, that's a copper fin tube boiler, and it was operated well below the dew point of the exhaust gases, and you could see major corrosion, not only inside the boiler, but the vent connector and so forth. You're basically destroying the boiler, and you're also going to destroy the vent connector piping. I've seen it literally in a matter of months where there are holes right through the vent connector piping because the boiler was operating on a sub-dew point of the combustion gases. So there are ways to deal with that. And one of the ways to deal with it is to put in what's called an anti-condensation mixing valve. And this is just a thermostatic valve. It's a high flow capacity. I don't want to tell you to go out and put in a domestic hot water tempering valve. In theory, from a temperature standpoint, they could probably help. The problem with those is they have very restrictive flow compared to a valve like this. So this has a much higher CV rating, and it's specifically designed to act as a anti-condensation valve. And what it's going to do when there's cool water coming back from the distribution system, it's going to mix that cool water with some of the hot water leaving the boiler to bring the temperature that goes back into the boiler above the dew point of the flue gases. And these valves can be ordered with different temperature settings. Usually the low is about 110 degrees, and they go up well above that. For a gas-fired boiler, you typically want to keep that inlet temperature at or above 130 degrees to prevent flue gas condensation. So again, as you're adding heat pumps to an existing boiler system, don't forget to protect the boiler. If it is a cast iron, steel, or copper tube boiler, you would need some means of protection. Now, this is a pretty simple way to do it. There are other ways to do it with motorized valves, with injection pumps and so forth, but this is one of the simpler, easier ways to deal with it.
Hey, John, we're getting really tight on time here. Real quick, we had one question come up. Do you know of any software that's available for estimating additional heat emitters?
Not directly, no.
I would assume that maybe some of the manufacturers for panel radiators and things like that have some sort of calculators on their websites. I'm not familiar.
Yeah, what you're going to find, I'm sure you can find calculators that will give you the output of their emitters at different water temperatures.
Yeah.
And then it's just a matter of, this is what I have, this is what I need, and just do that calculation. So to answer your question, yes, you're going to get partway there, but I don't know of anybody that has a complete package from A to Z to do it all.
Yeah, I'm not familiar with one either. We did have one other question asking about defrost cycle and the air to water heat pump. Defrost cycles are just a necessary evil. On our particular unit, the kind of the most productive defrosting time or the most where you're going to do the most defrosting is really from 45 degrees down to low 30s, just above there. The colder it gets, there's not a lot of humidity in the air to really plug up the coil. So that's really, just above freezing is where you're going to see a lot of that happen. With our particular systems, I can only really speak to ours. Generally our defrost cycles last anywhere from 6 to 8 minutes. So it really doesn't impact the comfort inside the home. John, do you have anything to add there?
Yeah, the thermal mass of the distribution system is going to handle it. And again, on your AV unit, as you've explained to me, you can either draw the heat for defrost from the electric backup, or you could draw it from the Turbomax tank. So that's one of the nice advantages, honestly, with air to water compared to air, is that the thermal mass that's available in a hydronic system is typically enough that you can draw the heat you need for defrost without affecting the interior comfort. With a ductless system, you don't have that mass. You're actually going to feel cool air on those indoor heads during defrost. The heat's got to come from somewhere to do it. I'll finish real quickly. This is just a 2-pipe cast iron system. You know, this could have been out of the 1930s. Let's say we're going to add a geothermal water-to-water heat pump to this. So I've kind of split it up here. I've got the existing boiler over there. I've put the anti-condensation valve in. I'm just showing a generic water-to-water heat pump. You'll see it's in parallel with the boiler. Each has its own circulator. There are check valves here so we don't get reverse flow. And in this case, they're both feeding into a hydraulic separator. Again, direct to load would be a different approach to this. In fact, as Justin was telling me, with the new WV unit, the boiler would pipe directly into the back of the heat pump, which is a pretty slick way to do it. Yep, that's coming up. That's next month. We've got the 2 heat sources. They both go to a hydraulic separator. And then over on the distribution side, I'm just showing how you could add a panel radiator. You could actually tee it into the takeoffs for the cast iron radiator. You could put a thermostatic valve in to regulate flow through both of them and use a capillary tube up to a knob. You could also do this with a zone valve and a thermostat if you want to do it electrically. But that's a simple way to do it. You know, here's just three cast iron radiators and 3 panel rads that have been added to supplement or to boost the output because we're going to the low water temperature. So I think I'm going to skip that. That's just a summary. You can see that on the PDF of the slides, just a summary of what we've talked about. I don't know if do we have time for any questions at this point, Justin? Or
we've got most of them ran through here. There were a couple that people asked questions for later, and so we'll respond to those in a follow-up email. Real quickly, next month we are going to be covering our new variable speed water-to-water unit. Internally, we refer to this as WV Rev J, just stands for water variable. It is running new A2L refrigerant. And as John kind of alluded to, a little teaser, we have it in a dual fuel option where we pipe a boiler directly to the back of the unit. So I'm excited to show it off. We showed off the physical unit at AHR last week. So anybody that was down there, if you came over and talked to anyone in our booth, we had one there to show. You know, for those of you that have maybe done a WV in the past, we brought that unit out originally in 2017. We have learned a tremendous amount. And I'm excited to share the new stuff and what we have coming very, very soon. So I look forward to that. Hopefully you guys do as well. I'll turn this over to Kevin and he'll wrap us up here.
Yeah, we'll have the WB out in Vegas too. So if anybody's in that area and heading out to the International Builder Show, we will be there. We are booth 8911. But that's going to do it for us today, guys. Don't forget to hang out for just a moment longer if you can and fill out that very brief survey. As usual, send out that post-webinar email, as we mentioned. That'll have the video of this webinar, the slides, and a document with all the Q&A that we've answered and maybe have not gotten a chance to get to. Don't forget to share or join our Facebook group and then share the registration link with your friends, family, and colleagues. But we appreciate you guys joining us today and hope you'll do so again next month. Have a great day.
Thank you all.
Thanks all.